Hi, my name is Julia Chatin, and on behalf of my co-authors, I'm very happy to present our project on concreteness and abstraction in mathematics education, a taxonomy of the semantic landscape. And this process has been quite a journey, so I want to take you through this journey with us. So, have you ever heard that mathematics is difficult to learn because it is too abstract? Myself, I studied mathematics, and I actually quite like the abstract aspect of mathematics because I always saw mathematics as something very powerful because it's universal, because it's general, and because it is abstract. But then when you talk with people and you try to understand what exactly they mean when they say this, they might not mean general or universal. They might mean it's abstract because it's unfamiliar, it's abstract because it's too vague or it's too formal, which is a bit less positive than this powerful aspect that mathematicians tend to enjoy. Then it follows the question of how can we make math more concrete? And here again, it's a bit unclear what we mean. Do we want math to be more visual, more tangible, more specific, more familiar? All those differences might also have some impact on how it helps people learn or not learn. So for us, it started a bit this conversation of, okay, what do we mean by abstract and concrete in math? And then we turned into looking at mathematics directly and the nature of mathematics. And here again, there's a bit from both sides. So some people will define mathematics as an abstract discipline concerned with the identification of powerful generalizations or the manipulation of meaningless symbols, which is quite abstract. But some people will say that mathematics is the result of our sensory motor experiences with the world, or that mathematics is what mathematicians do and includes space for imperfections. And this is more on the concrete side of things. Now, if we look not just at the nature of mathematics, but also how we teach and learn mathematics, there is this concept of concreteness fading that argues that we should teach mathematics starting with concrete representations and then moving to abstract representations. And usually here by concrete, it means visual, but also something that can be manipulated and interacted with. And then the more abstract condition is something more symbolic, but there is also in the middle like a visual representation that embeds some meaning. So from this, we make our first claim, which is that concreteness is at least a spectrum. So it's not concrete versus abstract, but it's concrete towards abstract. But then that's not enough. So for example, in 2008, there was a study looking at how concrete representations can help students. And they made this representation for groups of order 3 and making some evaluation of learning outcomes, they found that such concrete representations were preventing transfer to more abstract representations. But then, in 2020, Terninic et al. Argued that this is not a very familiar representation because when you add a full cup to an almost full cup, usually what happens is that you get a full cup and a lot of water on the table. So they adjusted the example a bit to what you can see on the second line here, when now the identity is represented by an empty cup. And they found by making the examples slightly more familiar, they could not find those results again on preventing transfer to abstract representations. And here already in this paper, they argued that there are different types of concreteness and we need like a more fine-grained and a more precise way of talking about concreteness. In some of my own work as well, I was interested in embodied representations and the role of concreteness in embodied representations. And we did a study on graph theory where we compared 3 different conditions. One more abstract on paper where you just write your solution. One on tablet where you get some feedback for your solution. So it's like something interactive that you can act upon. And then finally, one in virtual reality that also has a more relatable or familiar example because you deal with water systems rather than just graphs. And here we found that both the manipulated types of concreteness created more satisfaction, but only the more embodied or familiar concreteness felt more relevant to the students. So here as well, I felt this is a sign that we need to speak of different types of concreteness because they might have different impact on learning. So from this, we make our second claim, which is that concreteness is actually multidimensional. And we were discussing this with Kenny, one of our co-authors who's a linguist, and he told us about the concept of verbal disputes. So verbal disputes are disagreements that arise partly or wholly in virtue of a disagreement about the meaning of certain words. Long story short, what we believe is that in our field, when we speak of concreteness and abstraction, we sometimes don't speak about the same things. So if we see different results or different implications, it might be because we're just not talking about the same thing. And our goal here with this paper is to identify and resolve those inconsistencies in mathematics education. So importantly, we don't want to find the best definition of concreteness, but we want to make the inventory of all the definitions that are used in the literature so we can have a bit of a more fine-grained approach to the topic. So our third claim here is that we do not use the terms concrete and abstract consistently. And our solution to this is we want to map the semantic landscape. So again, we want to make the inventory of all the definitions that are used. Because we used a qualitative method for this project, I want to quickly show our perspective statements. So we had one research assistant with a background in psychology and little to no experience in the field of concreteness and abstraction. We had a linguist, again with little to no experience in the field of concreteness and abstraction. And then we had two experts, one in embodied mathematics, who does have experience in concreteness in mathematics education, and one expert looking more at those kinds of concepts in chemistry, which we will see later became very useful in that project. So first we built our corpus using those search strings. This gave us 368 papers after cleaning. Then we implemented a little app to annotate the papers, and in the papers we only looked at the paragraphs that include the words related to abstract and concrete, and then as coders we had to tap on the words that highlight the specific definition that the authors are using. And then R3 and R4 defined the taxonomy. This was a qualitative approach over the various iterations. You can read in the paper if you're interested in that part. Okay, so how does the taxonomy look like now? So the first thing we noticed is that there are different ways of talking of concreteness, in the sense that some are subjective and some are objective. So what we mean here is that some are about the interaction of the learner with a certain representation. So for example, familiarity, that depends on the learner, because again, for me as a mathematician, symbols are very familiar and probably even more familiar than some of the examples that are used in mathematics. However, to someone who did not study mathematics, the symbols are very unfamiliar. So this depends on the learner. And then there are some more objective dimensions that have to do about the mapping between the concept and the representation. So for example, if the representation is physical, that means like implemented with a physical object, as opposed to virtual, that's a decision of the design of the representation, and it doesn't involve the learner. It will be physical with or without the learner. So again, what's important to know here is that we have some subjective access and some objective access. And then, in that context, we identified 5 axes at the subjective interaction level and 6 at the objective and mapping level. And if you're interested in all the definitions of those axes, you can check the paper. But here are some examples of codes that relate to each axis. I want to highlight again the difference between the subjective and objective axes. So I mentioned physicality, which is the lowest one here on the objective side, which is the decision of, do I make my representation a physical object or a virtual object? But then at the subjective level, we have sensoriality, which is, can the learner experience the representation with their senses? And this depends on the learner, because some learners might be able to perceive visuals and some learners might not. So even if you design your representation visually, that doesn't mean the learner will be able to leverage those cues. We then used our our taxonomy to classify certain use cases. So if we go back to the examples I mentioned before, we can now see that these representations with the cups, they are both situated in the sense that they use real-world examples. However, the one of Ternenich et al. Is more familiar than the ones used in the other studies. So, yes, they are concrete in some way, but they're also abstract in some other ways. And I think this starts to show the importance of the taxonomy. If we look at my own work now, we can see that actually the level of concreteness varied along much more dimensions than I initially thought. I also want to go back and speak a bit about concreteness fading, where here again we can see that yes, the three representations that are commonly used are organized from concrete to abstract or abstract to concrete. However, we can also see that different levels of concreteness are changing when you change the representation. And what was quite interesting here also is that we notice that concreteness fading leverages a lot of axes that are at the mapping level. And then, therefore, they are domain dependent. And again, I mentioned that Charlotte, who's a co-author here, is from chemistry. And that means that if we want to do concreteness fading in chemistry, we might change more about the representations because it is very domain dependent. One thing I want to stress as well is that the learner is important. So the learner is important, of course, for all the subjective axes, but even when we look at the more objective ones, different decisions might have different outcomes for the learners. So for example, if you decide to have a physical over a virtual representation, that might be good for neurotypical learners, but not so good for learners with ASD. So something to consider. In the paper, we also start discussing the relationships between the axes, because in that paper, we really wanted to just highlight all the meanings, and we felt it's a bit out of scope to start compressing some of the meanings or simplifying the taxonomy. This should be a different project that is more like guided by practice. But still, we already started mentioning some connections. So for example, if I make my representation a physical object, it is more likely that it will be experienced with more senses from the learners, so it will result in more sensoriality. Similarly, if I use a representation with high situatedness, which means it uses examples from the real world, it is more likely to be more familiar to the learner. And those kinds of relationships would be interesting to explore to see what the taxonomy can say about designing those representations. So now, in terms of future work, the things we would like to do are a meta-analysis that is informed by this taxonomy, so have an understanding of how all those axes impact learning outcomes or affective outcomes. Also the refinement of the taxonomy through expert interviews to identify the axes that are actually most relevant when you design the representations. And this will help towards the simplification into a design tool. And then we would be very excited to look at other fields, so for example, chemistry. Because one aspect that comes often in mathematics is, oh, we want to use a real-world example, which is a situatedness axis. Well, in chemistry deals with the real world, so an atom is real, however, it can feel very abstract because it cannot be directly perceived. So we believe that in other domains, those axes will be slightly different and even inverted sometimes. If you want to use the taxonomy, in the paper, in the supplementary materials, we give several templates. One template to reflect about the connections between the different axes, one template to classify your own representation in the taxonomy, and one template to compare different representations in the taxonomy. And on that note, I hope you found this interesting. We are very excited to see what you do with the taxonomy. You can follow the project here, and yes, looking forward to future work in that direction. Thank you.